Hello and welcome. Today we're going to talk about Fourier series and we're going to perform an example computation. So recall what a Fourier series is. We have f hat and it's equal to a0 plus the sum n equals 1 to infinity of an cosine n pi over L x plus bn sine n pi over L x. Okay, and this we can take x to be on the interval negative L to L. All right, and this is our f of x, or f hat of x, and we have from our convergence theorem that f hat minus f is equal to 0 if f is piecewise smooth and f hat equals the periodic extension of f wherever f tilde is continuous and f hat equals the average value of the periodic extension at the left and right limits where f tilde, the periodic extension, is discontinuous, i.e. at x equals a discontinuous point. Okay, so again the idea here is if you have a discontinuous point, f tilde, the periodic extension, and f hat, the Fourier series, are equal to each other wherever f tilde is continuous, but at points where there's a discontinuity, that point right there, f hat, the Fourier series, takes the average between the two. Okay, and otherwise though, the Fourier series does pretty well. Okay, so that's the idea. So now we're going to compute computations, and we know that an and bn and a0 are the orthogonal projections. Okay, so let's compute this for an example value. So let's start with an f of x. And it's going to be defined on the interval between negative pi and pi. All right, and it's going to equal the following function. It's going to be 0 for x less than pi over 2, and it's going to be 1 for x greater than or equal to pi over 2. All right, so what does this look like, this function? If we were to draw it, it looks like, so here's 0, there's negative pi, and there's pi over 2, and it's going to be 1 for all of those values, and it's going to be 0 for all of these values. Okay? All right, so we can put a little dotted line there. So there's a discontinuity, but we know that is it going to be f in this case is piecewise smooth because it's continuous and its derivatives are continuous on everywhere but finitely many points. And there's only one discontinuous point with f. And so what about the periodic extension? What we want to do is compute the, we want to just plot what the periodic extension looks like, and it's pretty straightforward. I'll just draw a picture. We go out like this, and make a big real line there. All right, we have 0 right there, and we have pi, and we have 3 pi, so on and so forth. We have negative pi, We go back, we have over here negative 3 pi. Okay, and so there's pi over 2 right there again, and it's going to go up like that. It'll be a little step. And then there'll be another one at another step right there. And there'll be another step right here at negative pi over pi halves. And another one here. So we see this is sort of like a periodic step function, like a periodic pulse. So in terms of some sort of a signal over time, this could be, you could think of this as like just a step pulse that we give every pi seconds, that we give a pulse that goes on for a quarter of the time over the whole interval. We just keep giving these pulses. So this could be any kind of pulse-like situation where such an application is required. So that's what the periodic extension looks like. So now what we have to do is compute the actual Fourier coefficients, the orthogonal projections. So let's start with A0. Right, remember that's going to be the function f projected onto the function 1 over the inner product of 1 with itself. Okay, so let's write down what that looks like. That's going to be negative pi to pi of f times 1 dx all over the integral from negative pi to pi of 1 times 1 dx. So clearly that's 2 pi in the bottom. And at the top, remember that f is basically 0 all the way up to pi over 2. So really we can write this as pi over 2 to pi of the function. The function value is just 1. So it's just 1 times 1 dx. And that's just going to be pi over 2 over 2 pi. So that becomes 1/4. Right, notice that A0 is this projection. This is also what we call the average value of f over the interval. Notice that's true. You see that it's 1, right, for 1/4 of the time. And it's 0 for 3/4 of the time. So the average value over the entire interval is going to be 1/4. Okay, so that's always true with A0. A0, that Fourier coefficient, always represents the average value over the interval. So now let's compute our function. So remember, we have our basis functions. It's our Fourier series, and it's going to be the set sine. And it's n pi over L. In this case, L is pi, so it's just going to be nx. And it's going to be cosine nx from n equals 1 to infinity. And we're going to union that with the function 1, which is the one we just computed, that Fourier coefficient. So now let's go on to the other cosine terms. And that's going to be the inner product of f with cosine nx over cosine nx inner product with itself. Okay, so let's write this down. This is going to be, again, pi over 2 to pi of, and we have over that interval the function value is 1, so it's going to be cosine nx dx. And the bottom integral is going to be integral from negative pi to pi of cosine nx squared dx. All right, so let's write this down a little bit further, take up all of our space here. So that bottom integral is going to be, we can use a trigonometric identity. It's going to be the integral of negative pi to pi of 1/2 1 plus cosine 2nx. Okay, that's just the double angle identity. And the top we can actually compute straight away. The antiderivative of cosine is sine nx. But then what we need to do is, of course, divide by n. Okay, and we're going to evaluate at pi over 2 to pi. And the bottom integral, we'll say the integral of cosine over negative pi to pi, that's going to be 0. And so we're going to be left with only 1/2 times 2 pi. Okay? And then what we have on the top then is we have to evaluate sine. We have 1 over n, which we can put out front, and a sine of n pi minus a sine of n pi over 2. All right, so the 2's cancel there, and we're left with 1 over n pi times, and this term here, n pi, sine n pi, that's always 0 for every n value. So we're left with a negative sine n pi over 2. So what does that look like? And if you pick different values for n, we can see that if n is even, that means an is going to be 0, right? Because even values will always lead to multiples of pi, and sine will always be 0 there. But for odd values, it's going to alternate between 1 and -1. So this is a pretty complicated thing. So an for odd values is going to be pretty interesting. It's going to be 1 for n is equal to 3, 7, 11, and 15, and it's going to be -1 for 1, 5, 9, and 13. It's pretty complicated. Anyway, that's what it is. We can, for every value of n, we can just evaluate this expression, and we're going to get some coefficient for it. So now let's go on to bn. So again, I'll just write that up there again. an. So actually, apologies. Here, so a0 was 1/4. We found that already, and then an was going to be equal to n pi negative sine 1 over n pi times negative sine of n pi over 2. Okay. All right, and that's going to be a very interesting expression there. So now let's do the bn's. It's going to be the inner product of now sine nx with f over the inner product of sine nx with itself. And that's going to be the integral again from pi over 2 to pi, because that's where our function is non-zero, of sine nx dx. And here we're going to get the same result as before. It's just going to be pi. All right, so it'll be pi down there. So now we need to just compute this all the way through. So the antiderivative of sine is negative cosine. Over n, evaluated at pi over 2, and pi. All right, and then we divide by pi down there. Okay, so let's go through this a little bit further. What we have here is a cosine n pi over 2 minus cosine of n pi all over pi. N pi, right? Because there's still an n down there, right? So there we go. So now let's just evaluate what these terms look like. So again, we have a0 is equal to 4. So now let's write down, and then we have this bn is equal to this complex expression. So let's see if we just get a sense for what this looks like. What do these coefficients look like? So so let's look at this term here. I'm going to look at the, so we'll take n is equal to 1, n is equal to 2, n is equal to 3, and so on and so forth. 4, 5, 6, 7, 8. Okay? And we're also going to make a table here where we're going to have here, this is going to be just the sine term, sine of n pi over 2. And that's going to be from that one. I just want to get a sense for what this looks like. And this will be the cosine of n pi over 2 minus cosine of n pi. All right, so cosine of n pi, this alternates between 1 and -1. So this is actually going to be, so when n is equal to 1, we get a negative number. So we can actually rewrite this as just -1 to the n power is a way that expresses exactly the same behavior as cosine n pi. This one's going to be a little bit more complicated. So again here, if I put n equals 1, I get pi halves, so I get a 1. Now if I put n equals 2, here I get 2 over 2, that becomes sine of pi, that becomes 0. And now n equals 3, I get 3 pi halves, that becomes -1. And this becomes n equals 4, creates sine 2 pi, which is 0, and then we get n equals 5, we get a 1, and then we get a 0, and then a -1, and then a 0, and so on and so forth. You see the pattern that it alternates between 1 and -1 for all odd values of n, and for all even values of n, it's just simply 0. Here, another pattern, maybe slightly more complicated, is, so we'll write this down. So when n is equal 1, cosine pi halves is going to be 0, and this is going to be -1, so it'll be -1, it makes it +1. Good. All right, and now for n equals 2, we have a cosine of pi here, so that becomes a -1 minus a -1 to the second power, which is going to be a +1. So that makes it negative, it makes a -2. Okay, pretty interesting. Now n equals 3, and 3 pi halves, that becomes a 0 again. And then we have here, it'll be a negative of a -1, which makes it a positive value, so it becomes +1. Now going down to n equals 4, we have cosine of 2 pi, which is going to be 1, and then minus -1 to the 4th power. All right, so that makes it a +1, that makes a 0. Okay, so this is pretty complicated. And you see it keeps going like this. We can keep going. Now we'll go to n equals 5. We're going to get 0 for this term here. And then we have a minus 1 to the 5th power, which becomes a +1. Right, and so it keeps going like this. This pattern keeps repeating. So you see this is pretty complicated, and it's not something we want to guess at quickly. I think you really need to go through and kind of write down a table until you see the pattern happening. All right, so there's where we go. So those are the coefficients, and we can write those down. And now what I'm going to do now is actually just use the Fourier series coefficients to see how well these approximations work. So what I did was I actually programmed a MATLAB program to plot our function f and its periodic extension and write down what happens. So here I'm going to go pull up my MATLAB and pull up my equation editor. So here it is. I'm going to run my program. This is just a little program that will plot my the periodic extension. So here's our little pulse function, okay? And we see here the values of pi and 2 pi and 3 pi and so on and so forth. And here's our little pulses that go on every pi intervals. So now I'm gonna do the first approximation. This is the n equals 0 approximation. So now that's it's at 1/4, 0.25. And now I'm gonna go to n equals 1. So I'm gonna include one more term in my series. And that's the n equals 1 term. So you see we're getting a better approximation, but still pretty bad. Now we'll do another one. All right, you see the Fourier series, these orthogonal projections, these terms, as we include more terms in our Fourier series, we're getting a better approximation. Things are getting a little tighter. N equals 2, 4, or n equals 3 and 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. And we can keep going. And you notice that there's these really high frequency oscillations that occur at the discontinuity points of our periodic extension of our pulse function. And that's generally why the Fourier series tends to converge less well at discontinuous points. And you see there's these sort of spiky, really high frequency wiggles that happen. And that has an actual name. It's called the Gibbs phenomenon. And it's a very common feature you'll see. So at n equals 100, we get a very good approximation for our pulse function. So again, you're looking at a bunch of sine and cosine waves, some of them very high frequency, but when you add them together in the correct quantities, as we keep adding more and more terms, our Fourier series is getting closer and closer to the periodic extension of our function. So that gives you a really concrete example of how Fourier series works in practice. So thanks very much.